Welcome to this video, which is about the derivative of a special function. In this video, we are going to find the answer of the question, that is why d/dx of e to the power x is again e to the power x. That is why the derivative of e to the power x is again e to the power x. We can easily show that is d/dx of e to the power x is again e to the power x by finding the derivative of e to the power x using the first principle. But here we want to show this one in another way, using the geometrical significance of derivative as an angle of tangent. For this, we need to know what is derivative and what is the geometrical significance of derivative as an angle of tangent. And finally, the graphical representation of derivative of e to the power x. Let's start with what is derivative. The derivative of a function gives the rate of change, or for a curve, its gradient. For a function y equal to f of x, dy by dx, which is equal to limit del x tends to 0, that is del x approximate to 0, then f of x plus del x minus f of x divided by del x. This one is called the derivative of f of x with respect to x, that is the rate of change of f of x with respect to x. This f of x plus del x minus f of x, this one is the rate of change of f of x, or we can say this one is the rate of change of y. Now, the geometrical significance of derivative as an angle of tangent. The slope of the tangent drawn at any point of any curve y equal to f of x is equal to the derivative of the function at that point. That is, if we draw a tangent at any point of any curve, that is y equal to f of x, then the slope of that tangent at that point is equal to the derivative of that function at that point. That is, for a function y equal to f of x, the tangent at any point makes angle theta with the positive direction of x-axis. Then the slope of the tangent at that point is tan theta, which is equal to dy by dx. The slope of tangent, that is tan theta, which is equal to dy by dx, that is derivative of that function with respect to x at that point. In this video, we are going to show the answer of the question, that is derivative of e to the power x is y again e to the power x, using this geometrical significance of derivative as an angle of tangent. That is, using this one, that is dy by dx equal to tan theta. Now, let's see the graph of y equal to e to the power x. That is the graph of exponential function. Suppose this one is the graph of y equal to e to the power x, because this one is x-axis, this one is y-axis. And for x equal to 0, the value of y is equal to e to the power 0, which is 1. And for 1, this one value is e, that is 2.718 approximately. And for 2, this one is value is e square. And for x equal to minus 1, that is 1 by e. So consider this one is the graph of y equal to e to the power x. Now, at x equal to 0, the value of y is equal to 1. That is, at this point, if we draw one tangent, this one will make the angle theta with the positive direction of x-axis. This angle is theta. In this case, that is at 0, 1 point, this angle will be 45 degree. If we measure this angle, this theta, the value of theta will be 45 degree. And we know then tan theta, that is tan 45 degree, will be the slope of this tangent. So tan 45 degree, which gives the value 1. Again, if we take the tangent at this point, that is minus 1, 1 by e. At this point, in this case, we get another angle. The value of this angle is approximately 20.1975 degree. And if we find the value of tan 20.1975 degree, which is exactly equal to 1 by e. And if we take this angle exactly, in that case, this value will be exactly 1 by e. At this point, that is minus 1, 1 by e, the value of slope is again 1 by e. Now, if we draw another tangent at this point, that is 1 e. In that case, we get another angle which is approximately equal to 69.8025 degree. And at this point, the value of slope of this tangent is tan 69.8025 degree, which is equal to e. If we take this angle correctly, that case we will get the value of tan, this angle is exactly e. So at this point, 1e, the value of slope of the tangent is again e. If we take another tangent at this point, that is 2e square, in that case, we get another new angle, which is approximately equal 82.2927 degree. So at this point, 2e square, the tangent makes the angle 82.2927 degree with the positive direction of x-axis. So tan 82.2927 degree, which is equal to e square. We just consider this one is approximate value. If we find the exact value of this angle, in that case tan, that angle will be exactly equal to e square. So at this point, that is 2e square, the value of the slope of tangent is e square. So we find the value of slope of tangent at this point, this point, this point, and also this point. Now let's see the graph of x by dy by dx. That is, if we replace this y by dy by dx, what will be the graph? That is, if we draw another graph where along x-axis we take the value of x, and in y-axis, that is in this vertical axis, we will take the value of the slope of tangent dy by dx, that is d dx of e to the power x. What happened in this case? Let's see. So this is the table what we already got from the previous part. That is, at 0, 1, the value of x is 0, the angle is 45 degree, so value of dy by dx, or the slope of the tangent, which is 1. At minus 1, 1 by e, the value of x is minus 1, and the angle is 20.1975 degree, and the value of dy by dx, which is the slope of the tangent, which is 1 by e. Similarly, at point 1, the value of the slope of tangent is e. At point 2, the value of the slope of the tangent is e square. So let's see the graph taking this x value and the dy by dx value. This one, the along x-axis the value of x, and along this vertical axis the value of dy by dx, that is the value of slope of tangent. When x equal to 0, in that case the value of the slope of tangent, that is dy by dx, is 1. So we got 0, 1, this point. Again, at minus 1, 1 by e, that is for x equal to minus 1, the value of dy by dx, that is the value of the slope of tangent, that is 1 by e. So we got this point, that is minus 1, 1 by e. That is for x equal to minus 1, the value of slope, that is dy by dx, which is 1 by e. So here this point, that is minus 1, 1 by e. For x equal to 1, the value of dy by dx, that is the slope of the tangent at this point, is e. So we get this point, that is 1 e. Finally, at this point 2, that is 2 e squared, the value of x is 2, and at this point the value of dy by dx, that is the slope of tangent, is e squared. So we get this point, that is 2 e squared. So for x equal to 0, we get the value of dy by dx is 1, so this point is 0, 1. For x equal to minus 1, we get the value of dy by dx, that is 1 by e, that is minus 1, 1 by e. So at this point, that is x equal to 2, the value of dy by dx is e squared. So we get this point, that is 2 e squared. So all this point, that is minus 1, 1 by e, 0, 1, 1 e, and 2 e squared, is identical with y equal to e to the power x. That is the graph of this function y equal to e to the power x, and the graph of the derivative of this function is identical. Let's see the comparison. That is, this one is the graph of y equal to e to the power x, and this one is the graph of dy by dx, that is d dx of e to the power x. So we can easily see that this two graph is overlapping graph. That is, two graph is similar one. So we can say d dx of e to the power x, which is again e to the power x. That is, the derivative of e to the power x with respect to x is again e to the power x. Now let's see the derivative of others function and why this e to the power x is exceptional. That is the special function for this case. That is, for the finding derivative, the e to the power x is very much a special function comparing with the derivative of others function. Most of the function have just one point at which the functional value and the derivative value are equal. Let's see it. That is, if we take the function f of x equal to x squared, at this x equal to 2, the functional value is 4. If we find the derivative of f of x, that will be 2x, and at this x equal to 2, the value of derivative will be 4. That is, at x equal to 2, for the function f of x equal to x squared, the functional value is 4, Also the derivative value is 4. So for this f of x equal to x square, we have one point where the functional value and derivative value are equal. And for f of x equal to x cube at x equal to 3, the functional value is 27 and the derivative of x cube, which is 3x square, at x equal to 3, the value of 3x square, which is again 27. So for f of x equal to x cube at x equal to 3, the functional value and the derivative value both are 27. So we can say most of the function have just one point at which the functional value and the derivative value are equal. But for e to the power x, the functional value and the derivative value are equal for all the value of x. This one makes the difference between the others function and this e to the power x. That's why we can call this e to the power x as a very special function in case of derivative. That is, for e to the power x, the functional value and the derivative value are equal for all the value of x. That's why we can call the derivative of e to the power x with respect to x is again e to the power x.